Hi everyone, welcome back. So lecture number 5 today. So quickly, again, what we talked about last time, we talked about ideal gas laws. So to talk about ideal gas, we need to make two assumptions. First is the ideal gas, the gas is thin enough so then their molecules are far away from each other, so you can ignore the interactions between molecules. Second, the size of each molecule is negligible. That means you can treat them as point particles. You don't worry about the volume of the size of the molecules. So with that, we came to the conclusion that pressure is proportional to the number of molecules, proportional to temperature, and inversely proportional to the volume of the gas. And if you rearrange the terms, the relationship among the parameters becomes P, pressure times volume, equals to number of molecules M times K, small k, which is constant number, times T, the temperature, where K is called the Boltzmann constant, and it's 1.38 times 10 to the minus 23 joules per Kelvin. And in chemistry, we use the Avogadro's number. So in that case, capital N now equals to small n, which is the number of moles, times Avogadro number M sub A times K times T. So then N times N sub A times K will be another constant called gas constant, universal gas constant R. It is the combination of 6.022 times 10 to the 23 and 1.38 times 10 to the minus 23. These two multiply each other. The result is 8.31, okay, joules over moles times Kelvin. So then the ideal gas law, or we also can call it the equation of state for ideal gas, can be written as P, pressure times volume, equals to small n times R times T. Small n being number of moles, R being the universal gas constant, T being the temperature. Now that's for ideal gas. Now in reality, your gas is going to be having volumes, and then they are going to be interacting with each other. So one of the approximations you can do to simulate real gas is by using van der Waals equation of state. So which it takes into account the volume of each molecules, okay, which is in the problem B here, and then the interaction between the molecules are including the coefficient A in the formula here. So it then becomes this guy. So this equation is called van der Waals equation. All right, so today we are going to look into the molecular level to see the relationship between the temperature of the gas and how does that relate to the so the pressure and temperature, they are the overall, right, the collective the quantity to describe the collective behavior of the gas. So we call these two as microscopic quantities. Now, how do these two relate to microscopic quantities such as position and velocity of each molecules in this collection of gas? Okay. So before we look into the microscopic view of the molecular of the gas, we again need to use some assumptions to make things easier when we are talking about the theory behind. So the first one is we are going to assuming the molecules are identical to each other. They each have mass of m, okay, and inside this container of volume V, okay, and we are also going to assume that they are point particles. Each of the molecules is a point particle, so we don't have to worry about the volume of or the size of each molecules. We are going to also we are going to also assume the molecules move randomly and then always obey Newton's law. So in this case, Newton's law apply. Thirdly, we are going to assuming that collisions with molecules and the wall are elastic. So that means there's no loss of energy when the collision happens, okay? So those are the three key assumptions. So Let's take a look on an individual molecular. So we are going to make things even easier. We are going to assume this is just a single atom molecular. Okay, so maybe say helium or argon in that case. So look at one of them. It goes in one direction. It hits the wall, one of the walls. The container might have 6 walls or maybe have some different number of walls if it depends on the size you have. And it will be bounces back. Okay, so initially this guy is having velocity v, and then when it bounces back, it's going to have velocity v prime. So this guy has the velocity change, right? So that means its momentum changed. So as it hits the wall and bounces back. So when that happens, there's change of momentum of the molecule here. So that means there's force acting on this guy when the collision happens or during the collision happens in a very short time period, like say in the microseconds or milliseconds, maybe 2 microsecond time scale. So then there's interaction between molecular and the wall when the two collide. So there's a force on the molecular as well, and on the molecular and also on the wall as well. Okay. So the force by the wall to the molecular changes momentum, the molecular's momentum. The force by the molecular to the wall then exert on the wall. So if you do that force over area of the wall, then that gives you the pressure the molecular exerted on the wall. Okay. So let's take a look on detail here. So for a particular molecular, okay, so we are going to assume this is a cubic container with each side being L. Okay, so to simplify our derivation of the relationship between the quantities here, microscopically and also macroscopically. So the pressure exerted by a single molecular on the wall, okay, on average should be equal to the force it exerts on the wall divided by the area. Okay, according to Newton's third law, the force the molecular exerted on the wall should be equal to its magnitude. It's the same as the wall's force on the molecular. Okay, so that's the other way around. So for the force, then it has to do with the um, momentum initial. So let's say this guy goes here in this direction to be initial. All right, so it goes in, oh, let's do this one. So it goes in this direction. So goes in this direction, hit this guy, and then comes back. Okay, so this is the final, this is the initial. So normally we would say to the left to be positive, so the initial is minus, final is positive. Okay, so what happens here is the momentum change, it will be initial momentum mass times the velocity, right? Now it's going in the negative direction, so negative, and then final. So you do this guy minus that guy, right? So that gives you delta P change. The time, how often does this happens? It has to do with this guy hit this one, the wall hit this guy. Now because it's elastic collision, so the velocity doesn't change. Okay, so it will now bounce back with the same velocity Vx. And you'll hit this guy, bounces back, okay, and then hit this one. So the frequency, how frequent does that happen? It has to do with the time the molecular travels back and forth. Okay, so the distance traveled by the molecular is 2L. For the time required for the round trip, then it will be 2 times L divided by Vx. Okay, so I'm going to switch my camera here so you can see the algebra here better. But you might want to have your PowerPoint slide open somewhere so you can compare, refer to the figures for the algebra here. Okay, so pressure by each molecule is equal to force divided by area. And force for the force. So let's take on the force. Take a look on the force first. Force is equal to delta P over delta T. Okay, we know delta P is minus 2 times mvx. Okay, divided by delta T, it's the time for the round trip of the molecular. So 2LV divided by, or 2 times L, just 2 times L, divided by Vx. Okay, so this is the denominator in the denominator, so you'll flip up, right? The 2 and 2 will cancel. So then this becomes minus mvx squared over L. Okay, so this is the force of the wall on molecular. Okay, on molecular. according to Newton's third law, F of the molecular on wall then will be equal to this guy, the same magnitude, but in the opposite direction, right? So it will be minus of that guy. So minus of minus. So that means this is mv x squared over L. So which says this force should be equal to that. Okay, so then this equals mvx squared over L on top. That's the force. And the area here, it's going to be because this is cubic, right? So the area of each wall is going to be L squared. Okay, so then this gives you mvx squared over this L will go down. Okay, so L to the Q, which L to the Q is the volume of the container, of the cubic container. So divided by V volume. So this is small v for velocity. This is capital V for volume. So pressure by each molecule on the wall, then it's actually equal to mvx squared over the volume. Okay, so that's what we have on the PowerPoint slide. So let's go back to the PowerPoint slide there. Okay, and let's see. So pressure by each molecule is equal to mvx squared over v. Okay, so we were just looking at the one-dimensional x in the x direction. Okay, and the same will happen in the y direction and z direction as well. Okay, so we'll just focus on x direction for right now. But overall pressure by all the molecules, if there's n numbers of molecules, right? So the m times p molecules equal to them n times of this term, n times of mvx squared over v. So then P overall P is equal to mvx squared over V. So if you multiply everything by V, you get rid of V here on this side, but you will have P times V on the left-hand side. So then PV equal to mvx squared, okay? And we can manipulate this, the right-hand side a little bit further. So we'll say we'll make a 2 here, and then we'll make 1/2 in front of mvx squared, because mvx squared, right? That's the kinetic energy. So let's just take the kinetic energy and turn out, and then we need to add the 2 to just make this equal to the initial expression. So then pressure times V equal to 2 times of m over times 1/2 mvx squared. Okay, so we are really talking about here in this case, this should be just the average kinetic energy of each molecules of all the molecules inside the container. Okay, so then we should denote AV for average, because each molecules may have slightly different velocities, right, at certain time. All right. So with that, then PV equal to 2 times m times 1/2 mvx squared, okay, and average. So we can also take a look at the one of the expressions for ideal gas law. So PV equal to capital N KT, all right, and then we will do the same thing here. We'll put 2 in front of m, but then we need 1/2 in front of KT. So then we get this 2 times m times 1/2 KT. So PV equal to this. PV is also equal to this guy, right? So then we can see this 1/2 mvx squared average is actually equal to 1/2 KT, okay? So that's the conclusion here. So on average, the kinetic energy of the molecule in one dimensional, so this is for x dimensional only, okay, is equal to 1/2 KT. K is the Boltzmann's constant, okay, and then T is the temperature of the overall gas in the container. Now, keep in mind that there's also y direction and z direction, right? And each direction should be what you have for the velocity, because it's random, right? It's arbitrary, right? So it could be arbitrary. So that means each direction should be identical, right? X, Y, and Z should be identical, because you can rotate the X, Y, Z axis however you want, right? As long as they are perpendicular to each other. So if kinetic energy on average in the x direction is KT, 1/2 KT, then it should be the same as in the y direction, and then also in the z direction, okay? in that sense. So for the kinetic energy of a molecule in all three dimensions combined, it should be equal to then the three energy in the three-dimensional combined. So each dimension has 1/2 kT. So then three-dimensional combined add up to be 3/2 of kT. So K average equals to 3/2 of kT. Okay, K with the bar means average kinetic energy. And if this is the only energy you have for the gas system, if the kinetic energy is the only thing you are considering, then internal energy of the gas as a thermodynamic system, it should be equal to n times of the kinetic energy on average of each molecule, right? Because there are n numbers of molecules. So 3 times of nkt. And we know if you use moles, small n, then it should be 3 times of nRT, okay, in that sense. So internal energy will be just determined by the temperature of the gas, okay, in this case, okay. So in here, we are relating the average molecular kinetic energy to the temperature of the whole gas as a whole. So this is a macroscopic quantity, but this is the microscopic quantity because this is the quantity, the velocity for each molecule, okay? And then temperature is for overall, okay? So there's a relationship between the two. All right, so kinetic energy average for each molecule is 3 times of kT. And then in that case, kinetic energy is 1/2 mv squared, right? Average, right? So then based on this, you can calculate what will be the average of v squared. So you divide both sides by 1/2 times m. So then v squared average equals to 1/2, we'll cancel the half down here. So 3 times kT over m. So 3 times kT over m. And again, so in this case now, from this point on, if you multiply both sides by Avogadro's number, okay, the numerator m and denominator by Avogadro's number, so then here you'll get, because Na times K will be R, so 3 times RT. And then this is Avogadro's number times the mass of each molecule, which gives you molar mass, okay, of the gas. So then V average can be also equal to 3 times, or V square average can be equal to also 3 times of RT over M. So either this one or that one. So in that case, if you take a square root of V square average, that quantity is called a root mean square speed of the molecule. So the root mean square speed of molecule is equal to square root of V square average. It's going to be equal to 3 times of RT over M in this case, or square root of this guy. So it's 3 times of KT over M. Okay, so it depends on which expression you use. If you use R, gas constant, then you are using molar mass down here. If you are using Boltzmann constant, then you are using the mass of each molecule. Okay, so pay attention to that. All right, so let's take a look on the example here. So this one says you have 1 mole argon gas is confined to a 1.0 liter container at a pressure of 10 atm. What's the RMS speed of the argon gas? Consider the argon gas to be ideal gas, okay? And then 1 atm is equal to 101325 Pascal. B, compare your answer to the root mean square speed of helium atoms under the same condition. Given molecular mass for argon is 39.95 grams per mole, and for helium is 4.003 grams per mole, okay? So let's take a look on this one. All right, so we are given, what's given here is the volume is 1 liter. So liters is not an SI unit, right? So you might want to convert this into SI unit of 1.0 times 10 to the minus 3 to the cube. It tells you the pressure is 10 atm. The pressure is 10 atm. Atm is not SI unit, so 10 times 101325 Pascal. Okay, let me just write those numbers down before I actually exit full screen mode. Okay. And it says there's one more of it, so n equal to 1. mole. Okay. And what else do we have? We have the mass, molar mass for molecular mass for argon. So M or AR, that is 39.95 grams over mole. Molar mass for helium, He, is 4.003 grams per mole. All right. So we are looking for in A, we are looking for what will be the RMS speed. Okay, so if you can go one slide back, VRMS, right, is equal to square root of, there are two expressions you can pick, 3RT over molar mass or square root of 3KT over M, over small m. Sorry about that. Excuse me. So since it gives us molar mass, okay, so we'll naturally use this guy. And then if we pick that one, R constant is 8.31 joules over moles Kelvin. Okay, so we are going to use this VRMS equal to square root of 3RT over M. So 3 times 8.31 joules over moles and Kelvin, and the bottom times temperature. Let's see what's the temperature here. Oh, no, we don't have the temperature. Okay, divided by the molar mass. So let me just write down here first. Okay, 39.95. But this is in grams, it's not in kilograms. So you want to do conversion to kilogram first, okay? And square root. All right, so the question we have now we have a trouble here. What would be T? Okay. All right, so what do we do? It says consider argon to be ideal gas. All right, bingo. So then if once you see ideal gas, immediately think about ideal gas law, PV equal to nRT. PV equal to nRT. Okay. So then, what do we have now? We have actually, we have M, we have P, we have V. So we can solve for T. Okay, no problem. Then, so T equals to PV over nR. Okay, you can plug in the numbers. So N is 1 mole, 8.31 for R. Again, at this point, I'm going to just ignore the units here. So 10 times 101,325 if I'm using all SI unit, right? So 1.0 times 10 to the minus 3, okay, for the V. Okay, so you can do that. And this number goes back to there, all right? But I always would like to maybe think more, take a look at this. So if I have this as 1, okay, so my RT is actually equal to P times V, right? So then I don't have to calculate T. I can use RT as just a combined quantity, right? Because you will have RT there in here. Okay, so then let's just do that. So instead of doing square root of 3RT, I'm going to do RMS equal to square root of 3 times PV, right? Divided by M, okay? So then square root of 3 times P, which is 10 times 101,321 SI unit. V is 1.0 times 10 to the minus 3, okay, SI unit. And then divided by 39.95 times 10 to the minus 3, okay, also in SI unit. So everything is in SI unit. So if we do that, then this one gives 276 meters per second for the RMS speed, okay? All right, now let's look at B. If we have helium, then what do we have? So if we have helium, what's gonna do change? If pressure is still the same, volume is the same, so the only thing change will be the molar mass, okay? So instead of using molar mass for argon, we are going to use molar mass for helium then. So for part B then, this then becomes V RMS equals to square root of, again, 3 times 10 times 101,325, 1.0 times 10 to the minus 3, over, instead of 39.95, you will have 5.003, again, times 10 to the minus 3, okay? So that gives you 871 meters per second for the RMS speed, okay? So apparently, the RMS speed is inversely proportional to the molar mass, right? So for helium, it's lighter, so it then will actually move much faster on average, okay? Then comparing to argon, argon on average moves slower. Okay. So now let's go back to the slide. And let's move on. So we have been talking about just one pure gas in the container. What happens if you have, let's say, two gases or more than two? Okay, so for example, air, right? Air mostly is composed of oxygen and nitrogen, okay? So about like 21% will be oxygen and 78% of the air will be nitrogen, okay? So let's say if you have two mixture of the oxygen and nitrogen, right? So then the overall pressure then is actually due to the pressure of each gas. Okay, so again, you have oxygen hitting on the wall here. You also have nitrogen hitting on the wall here. So each type of molecules will exert a pressure on the container's wall, but the overall pressure of inside the container here will be the pressure by the oxygen molecules plus the pressure by the nitrogen molecule. So this is called Dalton's law. So or also called Dalton's law of partial pressure. Okay, so it states that the mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressure of individual gases. So P total equal to P1 plus P2. Okay. And for any two gases in equilibrium in a container, the pressures are also proportional to their molar masses. Okay, so P1 over N1 is equal to P2 over N2. Okay, so for example, if you have 21% of oxygen, then the pressure comes from oxygen will be just 21%. And then if you have 78% of nitrogen in the container, the pressure comes from the nitrogen will be 78%. Okay, so it's just proportional to the number of the compositions you have. Okay. All right. Another thing you might encounter here is, so we have an ideal gas, right? So now, although we say considering ideal gas, then you can ignore the interaction between them. But for real gas, let's say if you have a real collection of gas, right? So they are going to travel, right? In random directions. So chances are two other molecules might collide each other at a certain point, right? Or that happens, right? So a term called mean free path, we use symbol lambda for that term. It's the average distance traveled by a particular molecule between it collides another molecules. Okay. So let's say it hits one molecule, so it bounces off, then you'll hit another molecule at later time. So what would be the distance travel on average? Okay. So that's the lambda. So this lambda is equal to, so we know the distance, right? Travel is equal to velocity on average times t. Okay, so let's consider, let's say, or let's do this. Let's say we have a molecule starting from here. It will actually, it has a radius of this guy. Okay. And then the other molecules, they will also have certain radius. Okay, so it will travel. So you can imagine two molecules, right? So one travel and then it might hit the other one, right? So when it hits this guy, so it's actually hitting there. Okay, so then the impact area of this guy is not just the cross-sectional area of it, right? So anything here will be hit, right? So that means anything somewhere here with the distance from this molecular to that molecular will be then larger than the diameter of that guy, right? So you'll be doing, so for this is molecular 1, this is molecular 2. So it will be doing the impact cross-sectional area should be having a radius of R1 plus R2, right? So if it's here, it hit that. If it's here, it will hit that. If it's somewhere here, right here, just touching, then it will hit that too, okay? So that's the actually the impact area, okay? So pi d squared d being the R1 plus R2, okay? So it travels through, okay, and then because we considering all the molecules are the same, so R1, R2 will be the same in this case, okay? And then it will be equal to the diameter of the molecular, okay? So actually that guy. All right, so then area equal to pi d squared in this case, okay? So when it travels in the time interval t, the distance traveled will be this much, right? So then we'll be actually looking at then what will be the volume of this impact area actually come across, right? Across this length of this guy. And then that divided by the numbers of the molecules you have per unit volume, which is n sub v. Okay, so this is the molecular per unit volume. Okay, so it will give you the all right. So then lambda will be equal to the total distance traveled divided by the total molecules that enclosed by this volume. So total numbers of molecules here should be equal to the molecular per unit volume times the total volume. So the total volume will be pi d squared times Vt for this cylinder. Okay, so cross-sectional area times Vt in that sense. So Vt and Vt will cancel. So lambda then is equal to 1 divided by molecules per unit volume times pi d squared. Okay. Now, in reality, we'll the other molecules, they are not stationary, so they are also moving around. Okay, so if you take that into account, then there's a factor of 1/2 of the square root of that there. Okay, so because they can be moving around, so then the number of molecules you encounter will be likely be more. So then there's that square root of 2 in there. And in the pure gas in the system, so R1 equal to R2 equal to R, okay? And then NV is equal to N over V. So if you do that substitution, and D becomes 2 times R, so then this will be becomes 4 R squared in this case. So there's a factor of 4. So 4 R squared, and then N over V, or V over N in this case, because n small n sub V is in the denominator, so that N and V will actually flip, okay, in that case. So if you have a collection of gas that has volume of V, and then you know the number of molecules of N, and the radius of each molecular, then the mean free path lambda is equal to volume, total volume divided by 4 square root of 2 pi r squared times n, total number of the molecules there. And for ideal gas, because PV equal to nRT, right? So, and then if you rearrange in the term, so starting from PV equal to nRT, it's easy to get that V over N equal to KT over P, okay? So then in terms of T and P, lambda as the free mean path is equal to KT then over square root of 4 or 4 times square root of 2 pi r squared times P being pressure, okay? The mean free time is simply the mean free path divided by a typical speed, which is the RMS speed. Okay, so it will be this guy divided by RMS speed. Okay, so that means what will be the average on average the time between each collisions of a particular molecule to another one. So KT over 4 times square root 2 of pi r squared P V RMS square. Okay. All right, so engineering applications here. So it says state of our vacuum equipment can attain pressure as low as 7.0 times 10 to the minus 11 Pascal, assuming, suppose that a chamber contains helium at this pressure at room temperature 300 K, estimate the mean free path and the collision time for helium in the chamber. Okay, so we are looking for lambda and the collision time, which is the mean free time. Okay, so how? All right, so let me switch my camera. All right, so it gives you P equals to 7.0 times 10 to the minus 11 Pascal. It tells you T is equal to 300 Kelvin. It tells you the helium atoms has diameters of 1.0. Okay, so then radius is d over 2. That will be 1.0 times 10 to the minus 10 meters over 2. Okay, so you can calculate lambda. It should be equal to kT Boltzmann constant times T divided by 4 square root of 2 pi r squared times P, pressure. So Boltzmann constant 1.38 times 10 to the minus 23 joules over Kelvin times 300 Kelvin divided by 4 square root 2 pi, and this guy square. So 1/2 10 to the minus 10 square, and times pressure 7.0 times 10 to the minus 11 Pascal. Okay, so plugging those numbers into the calculator, it tells you 1.33 times 10 to the ninth meters. So that's the mean free path. Okay, so it's quite some distance. Good. And tau, mean free time, is the mean free path divided by RMS, VRMS. Okay, where we can calculate what will be the VRMS this time. So VRMS equal to square root of 3RT, okay, over M. So 3 times 8.31 times the temperature is 300 divided by 4.003 10 to the minus 3, okay, kilogram per mole, and square root it. So 1367 meters per second. So then this equals tau equals 1.33 times 10 to the 9 over 1367 meters per second. So that gives you 9.73 times 10 to the fifth seconds. Okay, so again, between collisions, the distance will be very long. The time interval will be very big. Okay, so that's a big number on time. So it's a very good vacuum in that sense. Pretty much nothing there. You can think about that way. Okay. All right. So let's talk about. So we'll actually skip section 2.3. We'll actually come back to that section later. But let's talk about the distribution of molecular speed. Okay, so quickly mention on that. So as I mentioned, the speed of each molecule is not necessarily the same all the time. Actually, it has a distribution of speed called Maxwell-Boltzmann distribution, and which the speed of the molecular is a function or the probability of the speed of a molecule at certain speed. Okay, so for example, speed at 200 meters per second here, it has a probability of this guy at this point, and speed of 400, it has probability of this guy. So this is a probability curve. It's called Maxwell-Boltzmann distribution. This is a probability of that. So you can see it's a function of t and the function of v. Okay, and then v here also, t also there. Okay, so if you plot it, it goes like this. And you can do derivative of this guy with respect to speed. All right, and then it turns out to be the most probable speed will be about here for different molecules. Okay, so you get different speed. It also has to do with the mass of each molecule. Okay, so take that into account. And if you are at different temperatures, then at lower temperature, the speed, most probable speed is going to be stay at lowest end, and at higher temperature, most probable speed is going to stay at the higher end. Okay, so in that sense. All right, so we'll stop there for today then, and we will come back next time. See you guys.